Hello, good afternoon. My name is Randall. I'll be your teaching assistant for this lab. And today we're going to talk about support vector machines and their implementations in Python. So the basic gist and the outline of the lab includes a recap of whatever was taught about support vector machines, the implementation of support vector machines, and we'll explore the kernels of these support vector machines and certain parameters and hyperparameters of these functions. Okay, and at the end of the lab, we'll talk about possible questions we can explore about SVMs. So something you can do by yourself for further reading, which can give you more enlightened or insight into these algorithms that we are going to consider right now. So let's begin. We'll start with a recap. So I hope you guys attended the lecture today. And we're going to start with something about SVMs. What do they stand for? So an SVM stands for support vector machines. So they're called support vector machines for a reason, because, for example, if I have, let's say I have, this is the line, these are some points, these are some other points here, here, here. What we want to do is that we consider these data points as vectors in an n-dimensional space. So it could be 2D, 3D, whatever you want, whatever the feature space is. So why we call them support vector machines is that the decision of how we choose this decision boundary is decided on certain objects, or we can say they are representatives of those classes. For example, this X can be the guy that is the farthest away in this vector space from these other people. So once you cross this guy, it's 100% almost likely that you'll encounter people of this type, X. And similarly for this dot here, the same thing. If you go down below, your likelihood of classifying as blue dot is going down and more towards X. What if you go here above it, and you will most likely classify it as a dot. So that's why we call them support vector machines, because these are the support vectors which decide this hyperplane that we build upon. Okay, and what is a support vector machine used for? In the traditional sense, when this was developed, I think in the 60s or 70s, this was used mainly for binary classification. So we have data points of color red and color blue or whatever we want, and we want to classify them. Now there are a lot of variations on this. We have regression models also for SVM called support vector regressions. And we also have multi-class support vector machines, which we'll talk about a little bit later. Okay. And the essence of this support vector machine is something called a hyperplane and a margin. Hyperplane is essentially the decision boundary, or the line which separates these guys, those two different classes. So that line also has to have some sort of margin. So how much you want to, and the margin is decided by the support vectors. Okay, so anything inside that margin traditionally should not have any data points in that. But later on, as you saw in the lecture, we also had these slack variables. So you can have things inside the margin, and we associate some sort of number. 0 to 1 means that it's within the margin but not crossing the hyperplane, and greater than 1 means it's crossing the hyperplane. So it's going over to the other class, right? So these are the two essential recipes of this thing, support vector machine. How does it work? Support vector machine, essentially, from the lecture, I hope you learned that we have to take this normal vector between those two vectors, and if you convert it into, and we want to maximize that distance. So we want to maximize that distance, and if you can convert it to the other way around, and it changes to a minimization problem of that normal vector W. So the norm of that vector plus some other regularization terms. So, and the traditional way and the most effective way that I know of is that they use quadratic programming to solve this, or also they use like Lagrangian. So, but that contains a lot more variables. So that's how it is. It is essentially an optimization problem, and that's all there is to it. Okay, now that we have a recap of the theory of SVM, we can try to see how this works with some generated data. So here I imported some library from scikit-learn dataset. This has these functions which generate random data. Okay, so here you can see like I've randomly generated data like this. This is red and this is yellow. And we can see here that suppose what is the thing we want to do here? We want to separate these two classes, right? What can we do? We can draw lines, right? These lines should actually create a barrier where if you cross one over the other, you go to the other class. So we can see like possible some possible solutions or possible how do you say, candidates for these lines. So these are some of these lines. But what do you see here? Like, what is the issue here? That sure we have a decision boundary, but the problem, what do you see here? So the problem here is that we can have the first problem, of course, is first problem is the hyperplane is not correct. So for example, it might have some other functions. So if you draw a line, draw a line here, like so the line is very bad. If you draw a line here, this is the wrong hyperplane. Why? It doesn't separate, right? There are some misclassification here and all. So, and it's going against the optimization. So this is the wrong solution. So that is one thing. We can't just draw random lines. And another problem is that you have this line. You can have another line which is infinitely small, delta small here, going along the same slightly delta higher slope. Same here. We can keep doing that. So essentially, we almost have infinite lines that can represent this hyperplane, right? So how do we go about with this? We want to choose that hyperplane which maximizes the margin between those support vectors. So there should be some single one unique line which has the maximal value for example, these might be support vectors, sorry. So we can see that. So from scikit-learn, we already have something called SVM, and we import SVC, support vector classifier. And here we're just using a linear boundary, okay, because the example we have given here is linearly separable. So let's do that. Let's run that. This uses the same formalization that we use in other classical machine learning models from scikit-learn. You import the class SVC, you fit that with the labels and the training set, and you get that object. And here is just a helper function to help demonstrate what that decision boundary is. Right, so we can see here, clearly this is the hyperplane that satisfies what we need, which maximizes the margin from these two classes. And look here, we can see that these guys are the two support vector machines. And we can also have, it's not just we pick one support vector machine, there can be many coinciding support vector machines. Okay, so that's one thing we can look into. And this is just a simple example from scikit-learn. So we can also have the coordinates of these guys. We can see from scikit-learn, the documentation is there. You get the coordinates of these support vectors. So if the algorithm, and if you believe that they're linearly separable and you have points and you have their coordinates, you get an idea of what these representatives are. So that also gives some insight to the data. Right? So this is a simple example. Now let's do something more complicated. In the real world, you don't get simple linearly separable data, right? So here, let's make, again, we're importing some libraries, some functions. These make like more nonlinear data sets. For example, here, these are some blobs. This is the moon. It has some intersection. These two labels. This is like a circle. So this is enclosed in the other labels. This is another helper function that helps us to plot all these decision boundaries and margins and all that. Right, so let's create this thing. Let's create a model that fit x, y. Plt dot subplot 131. Yeah, 131. Plt dot scatter x 0 x 1 c equal y s equals 50 c map is equal to bottom plot SVC decision what function? Decision function. Okay. The model. Linear model, right? Let's name this plt dot title linear model, and let's do the same for these guys. This here and this here. This will be polynomial fit. This will be an RBF model. SVC RBF SVC equal to poly, right? Here should be RBF model, F model. It should be poly model, right? This should be 133, 32 linear model, RBF model, blah blah blah. It looks good. I think looks fine. So okay. So we have those three data sets, right? And we're using different kernels here. So this is the linear model. Looks great, like it perfectly fits this. Same thing here, RBF model also. So they find the best fitting decision boundary. So linear model obviously is linearly separable, so it just draws a line essentially. And polynomial also, it's a polynomial function, but we have to know that the best fitting polynomial is not a higher degree polynomial, but actually a line. And the RBF, so what the RBF does is that it takes an exponential of the norm distance of 2 points, x1 and x2, and it takes an exponential function. So what does that mean is that the more similar you are, the more you have, the more you are within that, the more the margin is surrounding that class. Okay. So this is an example, and this is another one for the moon type. You can see here it's linear doesn't work here, right? Because there is no support vector, like there is no vector here that decides exactly there is a shift from one class to the other class. And oh, I didn't change this. Did I change this? There's a problem here. I did this here. Okay. Okay. Yep. So you can see that here. So you see how what RBF is doing, it's essentially projecting your data set to a higher dimension. So if you imagine these points here, it's projecting them like that, and it's forming these clusters around that. Because what is it? It's sort of similar to k-nearest neighbors, where you're comparing the distances, and then based on that, you assign labels. So essentially it's doing that, and then drawing that decision boundary. Okay. And polynomial takes like a higher degree polynomial it thinks that it's much better than the linear fit. And yeah, we can see that here also. This is for the moons. See, an RBF again, like it makes a better decision boundary. It's projecting it to a higher space and then saying that, okay, this is a better thing. Polynomial does this weird thing here. So you can see like it's going with the data, but then again, it seems like the influence of these red points are drawing the decision boundary more than the influence of this yellow points. So there could be something going on there. And the other one is for the circles. It completely fails linear model. RBF again does well. So you can see like in these simple cases, just very simple cases, linear model, polynomial model, they're failing, but the RBF, it kind of adapts to the data set. right? But the problem with kernels is that it is what is a kernel? It's essentially a function that takes a vector and compares some distance and outputs and throws out some number. Okay, so there we have to choose various kernels for all these data points, and we have to keep an account of it in a matrix form. So that is computationally expensive and also memory inefficient. So it takes more time to load up and train. Okay, so we've explored those kernels. So now we go on to explore like the parameters. Okay, there are some, if you remember in the minimization formalization constraint for SVM, we have a half norm of that W, the normal, plus some regularization term, right? C and the sum of those slack variables, gamma. So C is essentially decides how much marginalization you want. For example, if you change the value of C, it means that if the value of C is low, you will give it more, you will be more lenient and won't penalize as much. So you can have some points which are not directly like on that margin, but it's like crossing the margin. So you're not penalizing. The misclassification error is a little bit higher. But if you have a higher C value, the margin will be much, much tighter. So you want as tight as possible. Okay, so that can also lead to overfitting. So we need to be proper. We need to think about how we choose these parameters. Okay, and gamma is, so gamma, what it does is it takes into account how do I decide this decision boundary based on what? Like, should I take all the data points in the whole data set, or should I only take very close values? So the lower the gamma value, the more the far apart points are taken into account. So you can think of gamma as maybe a localization of this algorithm. So it forms clusters and boundaries around these data points and margins around these data points. I'll show you an example. So let's see here. So this is just a function which takes a kernel and like plots it. So let's do an RBF. Okay. Let's see first with C1 and gamma 1. What happens? Looks good, right? So C1 is a bit lower on the lower side. So you have more what do you say, more misclassification on the, you can see these red points, they're crossing the margins, right? The yellow points also are crossing the margin, and some of them are even crossing the hyperplane also, like this guy. So a lot less penalization if C is equal to 1. So let's go to 100. Let's see what happens. See the margin, it's getting like tighter and tighter as we increase, right? You can think of this as the regularization term you see in Lasso. It's kind of the same idea. And let's see what happens when we change gamma to 100. Look here. So see, like it's taking into account only points which are close to the potential hyperplane that we are choosing. So if we're mapping those data points to a higher dimension, and we're taking a boundary, right? So, for example, here, but we're only taking, when our gamma is very high, we're only taking the close points that boundary. So you can see these very dense points here, right? So that is essentially the margin. So it's kind of localizing these sort of clusters here. Margin you can see here, right? So anything that is within that is almost 100% sure to be a red label, and the same thing with this guy, right? So that's what gamma does. You can play around with this more. And essentially that is all about the lab we're gonna talk to today. A quick recap of the lab is that we talked about the theory behind SVM. What are the different components of it, hyperplanes, the margins, and also the different kernels that are being used. And we saw through implementation through scikit-learn how these are implemented. These are the most efficient ones that I'm aware of, the implementation part from scikit-learn. If you find other ones, please let me know. So that's all for SVM. And some questions you can consider about SVM is, what will the decision boundary be like for support vector regression? So for two classes, we have this point in the middle, right? What if we have a regression and we have like, what are we doing here? What are we supposed to do here? So we want to do something, the decision boundary will be actually the function that we want to fit. You can think of it that way. So that's something to think about. One thing I also wanted to explore was this guy gamma and C. How do they influence each other? Do they influence each other? Is there some correlation when you're minimizing these things? I'm not sure, so you can look into that. And the other one is about multi-class SVM. So how do you draw a decision boundary? How do you optimize that when you have multiple classes? So it's not just these support vectors of two classes and the distance, right? The perpendicular vector from those two classes. We have to consider other classes also. So should we compare two classes first and then make a decision, and then that decision can be an input to another class, comparing that to another class label, something like that. You can look into that also. And another problem with SVM, or I'd rather say like something you can look into, is does it scale well? So what happens when we have a high dimensionality, the huge feature space and large number of training samples? So of course, like it will for sure affect gamma and C, right? And these margins that we form, like especially gamma, and marginalization error also. And when we're optimization, the problem is that I'll just give you a hint also how this can affect like number of training samples, because we're doing a Lagrange multiplier, so high dimensionality also. So if you have more and more equations and more, because remember what we're doing in the equation, we're minimizing with summation of those slack variables, and those are dependent on the number of training samples. So when you increase or decrease that, something's going to happen to that optimization, right? The optimization formalization. So think about that. So that's all for the lab today. I hope you guys learned something. And if you have any questions, please feel free to contact me. And that's all. So thank you very much. Have a good day. Bye-bye.